So this is question 50 from the GATE 2020 EC paper, and in this question we are given a sequential circuit with two flip-flops and its timing parameters and two combinatorial elements with their timing parameters. We are asked to find out what the maximum clock frequency, that is the frequency of the clock input, at which this given circuit can operate reliably. Underneath the question, you will find the title of the NPTEL course or video that is relevant to this topic. So let us proceed with solving this problem. In this problem, we are given flip-flops 1 and 2 with their propagation delay, setup and hold times given here, right? And of course, we are given two logic gates with their propagation delay. We are asked to find out what the maximum clock frequency, that is the minimum clock period at which the circuit can operate reliably. We are asked to find it in megahertz rounded off to the nearest integer. Now, of course, in any sequential circuit, finding the maximum clock frequency at which this can operate reliably is simply down to a task of finding the delay of the critical path. The critical path, of course, is the longest combinatorial path from an input to an from an input of the combinatorial circuit to an input of a flip-flop. Okay, so let us look at the critical path analysis for the following sequential circuit. Remember, we have to start at the output of a flip-flop and end at the input of a flip-flop and accommodate for the propagation delay of the source flip-flop and the setup time of the destination flip-flop, right? Even though the hold time is provided in this problem, it is most likely it's not necessary. It's most likely just a misdirect, right? So let's first look at path 1, which corresponds to originating at the first flip-flop, going through the two combinatorial gates, and then arriving at the second flip-flop input. The propagation delay is 3 nanoseconds. The propagation delay through these two is 4 nanoseconds, and the setup time for the destination flip-flop is 4 nanoseconds. So this corresponds to 3 nano plus 4 nano plus 4 nano. Let's call this path 1. So T path 1 corresponds to 3 plus 4 is 7, and 7 plus 4 is 11 nanoseconds. So that's the first path. And of course, the only other path in this circuit that starts at the output of a flip-flop and ends at the input of another flip-flop is simply the short of the output of flip-flop 2 to the input of flip-flop 1. But remember, it doesn't mean that because there's no delay in this path, it doesn't mean that because there are no combinatorial circuits on this path, that this path has no delay. Remember, we have to accommodate, or we have to account for the propagation delay of the source flip-flop and the setup time of the destination flip-flop. So this path indeed has a delay of 8 nanoseconds and plus 5 nanoseconds. So if we call that path 2, TP2 is 8 nano plus 5 nano, which is 13 nano. So the second path, which actually had no combinatorial elements in it, seems to have the greater delay. So the critical path, of course, the delay of the critical path is equal to max of TP1 comma TP2, which is 13 nanoseconds. And Fmax is 1 by TDCP, which is this value in gigahertz, and rounding off in first bringing it to megahertz, and that is putting the decimal point like that, and then rounding off to the nearest integer gives us 777 megahertz, which is in fact not 777, which gives 77 megahertz, which is the answer to this problem, 77 megahertz.